Thank you for joining this video about physical science. We're doing lesson 4, chemistry. We're going to be closing out this lesson with talking about 4.6, organic chemistry. Specifically, I'm going to go through some of the different types of molecules that they go over in your study unit, because we don't go over them all in your review video that's on your student portal. So organic chemistry is the study of molecules that contain the element carbon. And we're looking now at hydrocarbons. These are molecules that are made up of carbon and hydrogen. Um, and we're looking at the idea of a homologous series. This is when they have similar structures, where the molecules are all exactly the same, except they have a different number of carbon atoms and then hydrogen atoms associated with them. So for example, we have methane, ethane, and propane. These are a homologous series, and that series can continue to get bigger. But they're all the same except for they just keep adding another carbon. So you have methane with a carbon that has 4 hydrogen atoms around it. So the idea is that carbon can form 4 bonds. So you can see that clearly here. It's got 4 bonds, 4 things hooked to it. And um, hydrogens kind of just act as a placeholder. That's how we can think of them for organic chemistry. If you need something to bond to a carbon and you don't have something specific that's bonding there, you just put hydrogens there to fill in all the spaces. So with methane, you have 4 hydrogens. With ethane, you've got a carbon surrounded by hydrogens, except there's another carbon hooked to it, and it's surrounded by hydrogens. For propane, we just add another carbon and its associated hydrogens. And this series can keep continuing to get bigger and bigger. So that's what a homologous series is, where it's exactly the same, but we're just adding a carbon and some hydrogens. And another thing about the structure of the atoms is we can have aliphatic carbons, where they're in straight chains, or aromatic hydrocarbons where they're ring-shaped. And this particular type of ring, like we're looking at, is also called a benzene ring. So we're going to look at some different homologous series. The first one is alkanes, which are also called paraffins. And when we have these series, we're given general formulas for them. And those formulas kind of just show the ratios of elements in each type. So it looks a little weird. For paraffins, our formulas are CN, H2N plus 2. So what that means is we can have any number of carbons, and if we put that number in for the ends, we're also going to figure out how many hydrogens go with it. So for example, if we have a paraffin that has 3 carbons, it has 3 carbons, and then we put the 3 in for the other N as well. So to figure out how many hydrogens, it's going to be H2 times 3 plus 2. So 2 times 3 is 6, plus 2 is 8, so that tells us there's 8 hydrogens. So if we have 3 carbons, we have to have 8 hydrogens if it's in a paraffin. Okay, so this formula is just for this type of molecule. So for some examples, the methane, ethane, and propane that we just looked at. Um, again, because carbon needs to have 4 bonds and it fills them up with hydrogens, as we add another carbon each time, we're going to get 2 more hydrogens. And you can see these follow the pattern. Okay, so if we have ethane, which has 2 carbons, so for hydrogens, it's going to be 2 times 2 plus 2. 2 times 2 is 4, plus 2 is 6, and we have 6 hydrogens. Propane is the one that we just did here, C3H8. So if we use this pattern where we have all the carbons and we just add enough hydrogen atoms, it's going to follow the formula. So we can predict the next one. If we have 4 carbons and we make butane, it's going to be C4 and then H2 times 4 plus 2. Okay, we're putting the 4 in to this point here in place of the N. So 2 times 4 is 8 plus 2 is 10. So C4H10 is going to be butane. So this series can just keep on going, getting bigger. We're not going to go any higher than that, but that's how it works. It just follows this formula because it follows this structural pattern. So those are paraffins, also called alkanes. The next one is olefins, also called alkenes, and their formula is CnH2n. So again, what we do is we put in the number of carbons, and that also tells us how many hydrogens we have. So if we have 3 carbons, our hydrogens is going to be 2 times 3. It's going to be 6. So some examples of alkenes are ethene and propene. And when we see the structures here, we can see why we get the numbers that we do. When you have these, you're getting a double bond between 2 of the carbons. And so you can see there's no hydrogens here under those ones that are double bonded because carbon can only have 4 bonds. So it has one on the top, one on the left, and then 2 where it's bonded to the carbon. So it doesn't need to have hydrogens hanging out down here because it's already bonded to the carbons. So each of those carbon atoms has a total of 4 bonds. And you can see the same thing over here with the propene. This one on the left just has single bonds, so it's got 4 single bonds, 1, 2, 3, 4. But these over here, these are double bonded, so they have 1, 2, and then they've only got 2 hydrogens here, 3, 4, because they don't need any more bonds done. So for the alkenes, you've got a double bond between any 2 carbon atoms, and then enough hydrogen atoms so that the carbons still have 4 bonds. So our next one would be butene. If we had 4 carbon atoms and they had a double bond, it would look like this. Or instead of this double bond being here on the end, we could move it over one and have it look like this. So both of these are versions of butene. So they would have slightly different properties. There is a different way to differentiate them when we're naming them, but we're not going to worry about that. You just want the general idea that um, these special things that determine what series we're in, they could happen anywhere along the carbon chain. So they could happen there, in the middle, or they could happen here at the end. And the next one in this idea is acetylenes. So these, the formula is C3H2N minus 2. So if you have 3 carbons, you're going to get 2 times 3 is 6 minus 2 is 4, C3H4. And the reason for that is acetylenes have a triple bond. So you've got this first one would be called ethine or acetylene. You'll see a lot of things that have two names with organic chemistry, 2 or even 3 names. But you can see it's got a triple bond. So each carbon already has 3 bonds here, so it only needs 1 hydrogen stuck to it. The next one, propane, same thing. It's got 3 carbons. 2 of them are triple bonded, so it's only got 1 hydrogen hanging out here. The one that's only single bonded has to fill up with hydrogen to make the rest of its 4 bonds. And then we could keep going and add more. Again, with butane, we've got 4 carbons, so now we have some options. It could be triple bonded on the end or triple bonded in the middle, and either way is still butane. It's still following the rules. Now, it does talk about petroleum products because these hydrocarbons that we're looking at it are things that are in petroleum products. So if you take crude oil out of the ground, you can get a lot of different products out of it. Gasoline and kerosene are both mixes of hydrocarbon molecules. So there's not like one certain molecule that makes up gasoline. It's a whole bunch of different hydrocarbons. But they are mostly paraffins and olefins in both the aliphatic versions where they're just in a straight chain, and there's circular versions where the carbons come around and join each other to make a circle. You'd find all those in gasoline. And when you take crude petroleum from the ground, it's not useful as is, but you can get all of these things out of it, and they do that by distilling it. So they heat it up, and different hydrocarbons start escaping it. And so the ones, oh, and this is one of the mechanisms that do the distilling. So you got these big towers. The things that escape it between 90 degrees Celsius and 200 degrees Celsius and then are recaptured. Those are a bunch of different hydrocarbons, and those are what make gasoline. So they raise it to that temperature. Everything that comes off of it becomes gasoline. They raise it a little higher. Everything from 200 to 300 degrees Celsius that escapes and is recaptured is called kerosene. And then what's left after that at the bottom is going to be lubricating greases and oils and paraffin waxes or asphalt, depending on what type of crude petroleum went into it. You could have different things left at the end. So that's how they get a whole bunch of different things out of petroleum. And that's why it's in this hydrocarbon section, because all of the things that leave it at 90 to 200 degrees and even up 200 to 300 are various hydrocarbons. So all of the ones we looked at were pure hydrocarbons, just carbon and hydrogen. Now we're talking about functional groups. So if you change the structure of molecules, you're changing their properties. You're changing how that molecule acts, how it reacts with other things. So adding functional groups to a hydrocarbon skeleton changes the properties of that molecule, changes what happens. So a very common example is alcohols. So instead of a hydrogen over here, we have this OH radical, hydroxyl radical. And having that on any hydrocarbon makes it an alcohol. And we could have a homologous series like we did before. So instead of methane, ethane, and propane, now we have methyl alcohol, ethyl alcohol, and prochyl alcohol. So those are a homologous series. You can see they're exactly the same, except they have a different number of carbons in their chain and some hydrogens to fill in those carbons. You can also have different styles of alcohols. So for example, glycerin is an alcohol, but it's not in that same group. It's not in the same homologous series as the others because it is different. Glycerin has 3 hydroxyl groups attached to carbon atoms. So it is an alcohol, it's just a different type of alcohol. And that gives it different properties. So um, glycerin is different than these other alcohols. It is more soapy. It's stuff that's used in soap and lotions. Some other things that we could do to get different molecules, if you start with an alcohol and then oxidize it, you can make other things, ketones and aldehydes for starters. So to oxidize it, that means from that alcohol, a hydrogen is removed, and the oxygen and carbon become double bonded. It's from the OH radical that makes an alcohol. So instead of an OH here, so this used to be OH, the hydrogen gets removed, and now the O just double bonds to the oxygen. So if you do that on the end, the carbon that's on the end, if that's where the OH was, you get an aldehyde. And if it's the second to the last one, so instead of the end one, it's over one here, then you get a ketone. So these both are things that you get when you oxidize an alcohol. Another thing you could do starting with an alcohol, which has this OH group, is to replace the H with something else. So with the aldehydes and the ketones, we just got rid of it. It went away. But you could also just replace it with something else, and you put something else there, and now we have what's called an ether. So an ether ends up having an oxygen in the middle of the chain, and there's no double bonds anywhere. So you're just somewhere in your chain, and you could have more carbons over here off to the side instead of this hydrogen, but you have it somewhere, at some point you have a carbon bonded to an oxygen, and then it's just bonded again to another carbon. So that's called an ether. And that's going to bring us to the end of it. There's a couple more details they talk about, so definitely read through this section. But that is a good review of the different types of um, organic molecules that they go over the structures for. If you have any questions about it, don't hesitate to contact your instructor.